it's my great pleasure to introduce Professor Benoît Perthame, who joined Economic Supreme 1983. I'm sure most of you, maybe more than half here students, not was born at that time. And he is really an international leader in applied mathematics, applied analysis, PDE, math biology, and he has numerous awards, including invited speaker in International Congress of Mathematicians 1994. Also, some of you were not born at that time yet. And he also was a plenary speaker at ICM in 2014. And he was elected to a member of the French Academy of Sciences in 2017. So really, it's an honor for us to have him here to give a tutorial, and he gave a talk last week. So for all the junior people, he's here until I think tomorrow, right? Yeah, so try to use the opportunity to check, to talk with giant in the field, to learn how to do mathematics, how to build your career. Okay?
Okay, thank you. Thank you for coming to this series of courses, which will. So my course will be on the mathematical modeling and the analysis of models, coming from the question of living tissues. And when speaking of living tissues, a special case you have in mind is growing cancers, growing tumors, which is an important question in medical science. And these pictures you see here represent tumors. On the left, you have two cuts of organs with tumors. On the right, you have two numerical simulations of growing tumors. I would like to just point out that this one is a cut of a cancer of bone, but the bone in question is a bone of a dinosaur. So we know that dinosaurs were dying from cancer hundreds of million years ago. By opposition to virus, you may be more conscious of virus these days. Viruses are very recent. I mean, viruses are on Earth since the beginning of life, but the fact that the viruses are dangerous for populations is very recent and comes from big societies where people meet and exchange virus, as you know. And this is a few thousand years ago. So we are not at all in the same time scale for disease coming from infections, let's say, and from cancer. So what are we speaking of? What are the ingredients which are to be included in modeling of living tissues? Of course, cancer is a question of cells. Cells which are moving. We will describe how they move a little bit later. It's also a question of their environment. They use the environment to grow, to divide, and this because of molecules and fluids which are around. And these cells have also capacity of organizing themselves. And so tissue are also a question of self-organization in active matter. Of course, in terms of medical impact, you know that for what we call advanced countries, Singapore is one of them, cancer is now the first cause of death. In Europe, 1.3 million people die from cancer every year. So this represents between 1/4 and 1/3 of the death causes, the second one being disease related to heart and blood vessels. The good, if I can say, the good information is that this proportion is diminishing now. It has been increasing for a long time, and now in most of the countries, it is decreasing. Very slowly, but it is decreasing, in particular because men are smoking less than before. But this is compensated by the fact that women smoke more than before. So this is the motivations for working on this question. So the course will be organized in I don't know how far I can go, but basically in this way. I will first tell you about the history of cancer, few ideas which come from the long time, and then I will tell you of the modern view we have of living tissue, and then we'll do mathematics around that. So the first natural attempt to describe a cancer, you say, I don't know very much about the disease. What I can do are differential equations. So the first idea you could say is that each cell has a rate of division, which is given by this parameter R. And you could say each cell will divide with this rate, and then you grow with an exponential. So very quickly, you understand that this cannot be true, because exponentials are growing extremely quickly. So let's say a division cycle for a cell is more or less 24 hours, a little bit less. So if you count, the numbers will become extremely large very quickly. So it cannot be that this is the only effect, that cells have an advantage, and for some reason they always divide and divide. There should be other phenomena which compensate. So many people have said, okay, if it's that, it's simply because there is a carrying capacity. I mean, cells need oxygen, glucoses, whatever, nutrients to survive. And so you have a carrying capacity, and for a long time, the belief was that there is a given carrying capacity in a cell, in a tissue, so that cells cannot expand more than that. And then they have been fighting between using the famous Verhulst law, this limitation, like in Fischer KPP, with this kind of rate. They have put powers here to get more parameters. Here you have only 2 parameters. So here we have you can have a third parameter, and in some limit of this parameter that you could put here, you get what is called the Combert's law, which is also from the 19th century, where you replace this by a logarithm. So in any case, what you will find, of course, is that the number of cells, n of t, is increasing. So at the beginning of the tumor, there are very few cells. There are mutations which create these tumor cells, and they divide. At the beginning, it's always an exponential growth, because n being very small, here you see that you are close to r times n. And suddenly, you have a change of convexity, and you go to the carrying capacity, to the maximum capacity. And you see that the Combert's law and the Verhulst law give you very different trajectories, which have the advantage that they are simple and you can fit parameters. You can fit free parameters with free data. For any patient, you have free data, you can fit free parameters, there's no problem. The only problem is that all these models are wrong. They don't tell you at all what is the truth of a tumor growing or tissue developing. The reason they don't give the truth is the following. In fact, when cells are dividing, at the beginning you have the exponential growth, and this nobody will discuss that. Cells are dividing, they have an environment which they like, so they will grow exponentially. But very quickly, they will miss oxygen, because these cells, they create these cells, when they divide, they create more and more packing, and the blood vessels are distributed somewhere. So when they've developed so much, the access to oxygen is very low, and then they cannot grow more than a certain carrying capacity. So this would be true, except at some point, cells will begin to say, I don't like this environment, I don't have enough oxygen, so they go to the necrotic state. They will die in a very bad way. They are under stress, and so they emit molecules, and these molecules, which are called vascular endothelial growth factor, VEGF, are molecules which have the property to attract new blood vessels. So this is called angiogenesis. It's a phenomenon which is very well known, and which makes that these tumors will suddenly have more nutrients, and they will be able to continue to grow further. So one idea for therapy to avoid cancer was not to kill the tumor cells, but to avoid this phenomenon of angiogenesis, to find drugs, molecules, which make that these blood vessels cannot develop any longer. So these are called anti-angiogenetic molecules. There have been many, many attempts to develop them. A couple of them have been put on the market. They went to phase 3, and the outcome is that they were not very efficient. So they were, the result was not as expected. It didn't allow to cure cancer, and there was many, many studies to try to understand what is the effect of these anti-angiogenetic molecules. So the reason why they think that fails is that the new vasculature, when you have a normal vasculature, it is well regularized, it is very well behaved, it is regular. The vasculature created by tumors are very erratic. They are very bad quality, and this makes certainly that the molecules could not access to the tumor because of this irregularity. And so there were models which were proposed in the same class of ordinary differential equations, the same ordinary differential equation that you have seen before, but which now explains this carrying capacity, where it comes from. And so the idea has been to say that the carrying capacity that we see in Combert's law, so people like the Combert's law for some reason, they think it is closer to reality than the Verhulst law, but you could take another one, doesn't matter. And this carrying capacity is now the result of two phenomena. First of all, the cells are emitting a chemical, this VEGF, which makes that the number of the carrying capacity increases because the blood vessels are developing, and this is proportional to the number of cells. And then there is a limitation by access to the information, and then there is a limitation like that when the 2/3 has to do with the ratio between surface and volume, and things, which makes that there is this limitation. So this is a model proposed by Untitled and his collaborators in Boston, and this has been very much studied by several persons, the mathematician in particular. I mean, this Untitled is a physicist; he doesn't care about any theorem, but about the effect that you can conclude from that in terms of, for example, of efficiency of the drug. So that is the model of Untitled. What you can prove if you is that in this model, n of t converge in time to a limit, and k of t also, which of course you obtain by putting this to 0. So 0 is always unstable, and you get the steady state. So this is a way to take into account the nutrients and the effect of angiogenesis in the cell, in the tumor. It remains that the result is still very far from what happens really, and the only advantage is that you can fit easily problems with very few data. You usually don't have so many informations about a particular patient, and so this is one way to do it. So, of course, when you think of carrying capacity, the first thing which comes to your mind is an invading front, is an invading species in a space without predators, as we see many now with global warming. And so, if you want really to explain the carrying capacity, you have to include space. You cannot do it simply without with just taking averages and reducing the problem to ordinary differential equations. So when you speak of carrying capacity, the first thing you have in mind is that space is important, as you see, by the way, in this kind of cut of tumors. So in some sense, you are in the domain of invasion fronts, which is very famous in ecology since Fischer and KPP, and so you go to the next step, which is to say that the growth of the number of cells is now resulting not only from limited growth by some carrying capacity, as we said before, but also by random motion of cells, like in traveling waves. So this is the next step. It has been used a lot. It has the advantage, again, that it is rather simple. You don't need to fit so many parameters. And it is possible, of course, to include that the carrying capacity depends on the environment that you can change. So we still are speaking about number of cells at a position, at a time t, but now at a position x. We have still the interesting growth rate, so in the division rate, which will give the exponential growth if cells are very, very little. If n is close to 0, you can negate this term. And this phenomenon, of course, is very well known. It has been, not only it is very well known in terms of mathematics, we know that it represents a growth of an invading species, but also we know that it gives, I don't remember if it's here, we know that it gives fronts these fronts which are propagating. So the Fisher KPP will give you a solution which is where the number of cells n is nearly 0 here, n is nearly 1 here, and this front propagates with a certain speed, let me call it sigma, and this speed is constant. So you can measure, you can compute it from the equation. Not only it is constant in terms of mathematics, but it has also been measured experimentally, by the way, in this case. It's very well known. There was a studies in the 50s where in some farms, I think this is, I'm not very good in geography. I think this is Czechoslovakia, or this was the Czechoslovakia. So in any case, they had a farm where they were growing muskrats, which are not European animals. They were imported from America for their fur. And of course, at some point, the muskrats escaped from the farm. So they know exactly when these animals escaped from the farm. No predators, because these animals are not present in Europe. They invaded all Europe, and the ecologists in the 50s could follow precisely the front of the muskrats. And you see here the map from the beginning to for 30 years. And what they could measure is that the surface is growing like a square, which means that the speed of the front is growing linearly. So this is the belief is that all these fronts propagate with constant speed. Okay, so this was very much studied, and it's only recently that this assumption has been, this observation has been completed by another observations. That is not always true, and there can be accelerating fronts, which are much less studied in mathematics than the traveling fronts. And the reason, so this observation comes from Australia, where again they introduced foreign species, cane toad, which was there which was introduced because the toads like insects. So they were in the cane field in Australia. They had many insects which they wanted to get rid of them. So they introduced these animals. And these animals were very happy of Australia, where they had no predators. And they invaded completely the coast where it's humid. Yes. And the thing, as you can see, the traveling wave have a speed which is increasing. And the reason is that the toads, which are the front of the wave, are becoming stronger and stronger and are faster and faster. So they adapt to the competition with the toads which are behind to be faster in the front. And this is now a very big subject in biology to explain how cells, bacteria, can adapt in a certain environment to be faster in this case where you have a front propagating. Mutations. So if you give a drug which kills certain cells, the other cells can use the fact that there is more room to develop more. And this is one of the most important resistance effect to medical treatment. So with medical treatment, you kill certain cells with certain phenotype, and the others will go over. So these fronts are not everywhere. I mean, this is the evolution. This is the basis of biology. Life is able to adapt to the environment. So it's easy to create systems like that. And what I would like to point out is that all you can do very easily on a single equation, when you couple, even with this simple parabolic equation, can become dramatic. It's more or less what happened in the talk, for those who were here last week, of Leonid Rizzik. You seem to create a second equation, which is simple, parabolic equation, but this creates dramatic effects because you lose comparison principle. And so whatever you want to do here, which is based on the comparison principle, will fail when you do this. It has the same feature than in the model of linear. It's not what is called a cooperative system. It's a real system, so you lose all these properties. I would like to also to add up that in this field, you can always go from the scale, which is here of the traveling waves, where you see a profile that you can compute, which propagates, to a more global scale. What you see is a front propagating, with always a beta sigma, by the way, but not in the same time scale and not in the same space scale. And this you do by rescaling. So here, in some sense, you are at the scale of individuals, and now you want to go to the scale of the full picture. So if you go back to this, what you're interested is the front of propagation of plague, of the bubonic plague in the Middle Ages, at the scale of Europe. So what you see is not a traveling wave. What you see is really front propagating. This you can give a mathematical understanding by doing this rescaling, where you have changed the scale in space and time, and where you have a new equation. And now, because epsilon is small, what you see is that n should be either 0 or k. So k becomes 1 in the next line. And so you have a domain where n equals 1, which is propagating into the zone where n equals 0, which is unstable. So all these things, yes?
What's the physical meaning of epsilon?
So epsilon here is that you change both the scale in x and in time. So you have to multiply by epsilon here, and so you have changed x in epsilon x and t in epsilon t, which means that the speed have not changed. So this is what is called the hyperbolic scaling. The speed have not changed. The speed of the frontier and the speed of traveling waves are the same.
This mathematical way to explain.
Yeah.
What's a biological way?
Oh, simply that you can look at a phenomena at the level of a cell, or at the level of experiments, which is 1 centimeter or 10 centimeter. And depending on what you look at, you will observe this or this. If you look at the phenomena at the scale of the full experiment, you will see a propagating front, which is stiff like that. But if you zoom with your microscope, you will see that.
Because Arbor has a PD, a physical domain, boundary condition, right?
Yes, in practice you have.
Space means your physical domain becomes changed too, right?
So really,
your physical domain becomes originally you're supposed to have a disk, right? With
yes.
One.
Yeah.
Do this change your new problem, the domain?
No, not really. No, I can show you pictures. No, not really, because what they do in experiment, you have what they do, spheroids or inoculum, where you put the cells in the center of the dish, and for a while you see the propagating front and doesn't touch a boundary. So for the time scale of the experiment, the boundary you don't see it. So this is a very good approximation of what you observe. So you don't need boundary condition to explain these propagating fronts. Of course, this is limited in time because every experiment is limited in time, but this is reasonable. So the conclusion is that all this is nice, is fine, but no medical doctor will never tell you, or no experimentalist, no biologist will never tell you what is the carrying capacity of a tissue. This notion doesn't exist in the language of medicine or in human biology. It doesn't exist. It's an invention of mathematicians. If you want to really, of course, if you ask a medical doctor, he will tell you it's very complicated, and all these phenomena you have on the screen, they should be taken into account. So not only you have what I told you is more or less solid tumors, but you have all these liquid tumors or blood tumors, blood cancers. Cells can move different way. Either they are pushed by the tissues, they have passive motion, or they are active motion. The immune system metastasis, resistance to treatment are important phenomena. Drugs and nutrients arrive through vasculatures. I told you about angiogenesis. Cells are not a single type of cells. They are cells which are quiescent, cells which are proliferating, those which are necrotic, who are dying. And then you have many scales because you go more or less from the molecule to an organ with many scales in between. So all this makes that life is much more complicated than Fisher-KPP equation, which is already very complicated, by the way. And so when you think about that, the first view you have is that all this lacks mechanics. Behind a tissue, which is like a solid or liquid, there should be mechanics. And this is the second part of this talk, of this course. What are the mechanisms, in terms of mechanics, which are behind tumor growth? So this is something which is extremely active now. I would say that since 20 years, there's become the most recognized modeling of living tissues. You have people coming, okay, mechanics and physics are always difficult to distinguish. I think it depends on the culture of the countries. It's more or less the same. So you have many people who have been involved in that, in terms of physics and mechanics. And there have been many mathematicians also who followed this picture. If to have a very simple idea in mind is that the control of tissue growth in general is related to a notion of pressure. So there is a notion of pressure in a tissue like there is a notion of pressure in a fluid. It's not exactly the same phenomena because molecules and cells are not the same thing, but the outcome in terms of dynamics are comparable. In particular, the notion of carrying capacity, which was important if you have a view as an ecology, is completely forgotten. And I think this goes back to an early paper of Ellen Byrne and Dirk Drasdow, who said what is controlling the proliferation of cells is not the carrying capacity, is mostly the pressure. If pressure is too high, cells do not like it and they stop proliferating. And this picture here is a picture I took from a colleague in Paris, Emmanuel Farge, where they have forced a pressure on the tissue, on a rat, and just by an external pressure, they could completely change the biomagnetic force. They did that. They could change completely the shape of the tissue, and not only the shape of the tissue, but all the molecular pathways inside the tissue were changed with all the aspects of the tumors. So they could show that by increasing pressure artificially, you can change completely a tissue. And there are other experiments where you can, on the contrary, reset the pressure so that the tissue changes shape to become a normal tissue. So in both sense, you can do that. So this is, if there is only one thing to keep in mind, is that the real picture of a living tissue is a fluid. Our organs are fluids, and they are run by pressure. How did they do that? So the first person, Bern and Drasdo, when they did it just purely from computing point of view. They just run computers with models of cells, and they discovered that if you want to fit the experiment, the best way was to fit experiments with controlling the growth of the tissue by pressure. But then this group of people in Germany and in France, Johanny Prost and Julie Scher, did experiments. And the experiment is simple. You take cells, you take a piece of meat if you want, and you impose a pressure on it. And of course, these cells are with nutrients as long as they have as much nutrients as they want to divide. So cells are dividing, and you compute the pressure at which they stop dividing. So if you increase the pressure, at some point they stop dividing. Even if there is nutrients, they could divide, but they stop it because the pressure is too high. And they also could compare different types of cells, so to different types of cells, say healthy cells and tumor cells, and you let them grow, and at some point they will react to the pressure, they will stop growing with certain rules, which depends on the type of cells. So cells which are more sensitive to pressure, they will stop dividing first, and the other will continue a little bit until the pressure stops them dividing. So with this kind of devices, they could completely prove that indeed there is a pressure, and the pressure is controlling the division of cells. And these people are very good in communication, so they invented the notion of homeostatic pressure. So these names come from this group of people, which of course have to do with no, I forget the pressure between different fluids. There is a name which is like that. So now I'm so much used to this homeostatic pressure that I forget the other name. But so they came with this name, which tells you what is the maximum pressure that a tissue can survive to. If you go above, cells begin to die. If you go below, they continue to divide. Okay, so now that I have tried to convince, I'm not sure I succeeded to convince you that a living tissue is controlled by the pressure, we have to go a little bit further. What is the real physiology of your body? Your body is made, firstly, of what is called an extracellular matrix. These filaments are biopolymers. They have some stiffness, and they make the rigidity of the tissue. Okay? And this sustains the tissue. In this, outside this extracellular matrix, you have water, what is called interstitial fluid, basically water, and you have cells. So you have different types of cells. Many types of cells in your body, and you have molecules, chemical species. So this is what is sustaining the living tissues. And so it's really a multiphasic flow. You have really different phases. And because this extracellular matrix is very rigid, it doesn't change so much, and it creates the solid aspect of the tissue. For example, in your bones, your bones are mostly done of extracellular matrix, and there are very few cells moving around. In a smooth tissue, it's the contrary. It will be very little extracellular matrix and many cells. So, for example, your brain has very little extracellular matrix. So all this depends on the organs you are looking at, but they are all made of the same way. When you have such a phenomena with different multiphasic flow, one of the questions which come naturally is, are these different species able to mix nicely each other, or will they create boundaries? In which circumstances do you create one or the other one? And this is a question which is very important. I don't have pictures here, but we worked with medical doctors working on immunotherapy. You know that now one of the most efficient ways to cure certain cancer, like the skin cancer, are immunotherapy. You boost the immune system. And when it works, it's because the immune cells are able to mix nicely with the tumor. If the immune cells do not do that, it's a failure. So they know already what are the reasons why immunotherapy can work or not. And this is the effect which is behind. So this is an effect of multiphase flow and mixtures of cells. Okay, so now that we know more or less what are the mechanical reasons behind tissue growth, let's go to the models which have been used. So the simplest model you can imagine is very simple. So it's like Fisher KPP. You begin with something very simple. So now you have to say the number of cells changes for two reasons. One of them because they are moving. But in Fisher KPP, you see they are moving randomly. Here, we'll not say that move randomly. They have a velocity, v of xt. And they divide and die, like in Fisher KPP. The new thing, which is, of course, the important thing, is that there is a pressure. Because of this extracellular matrix which creates the rigidity, you are in a porous medium. Okay, so the mechanical view now of a living tissue is Darcy's law. You have a porous medium. So you say that the velocity is minus the gradient of the pressure. And you have to close. So the simplest way is to close by a compressibility condition, a law of state, pressure law. And so, for example, you can take n to the power gamma if you want to take a simple rule for the pressure, which, of course, you can question in terms of biology. But this is the new picture. You have this type of porous medium equation, and it remains to say what are the right-hand side. And this right-hand side has to do again with pressure, because what we know from Bern and Drasdo and from these experiments by Johanny Posch and Julie Scher is that the growth rate is controlled by pressure. So our basic model now becomes porous medium equation plus a right-hand side, where the right-hand side is decided by a growth rate which decreases with the pressure, because we say that the cells do not like high pressure. So you have this homeostatic pressure here, where the cells stop dividing, G of pH equals 0, and the function G is decreasing. Okay, so this is basically the model, the simplest possible model, which includes these new ideas that we have, that it is a fluid, and the right-hand side is controlled by pressure, contact inhibition. Okay, so this is the simplest model. This simplest model is not completely wrong, in the sense that if you look at what you obtain in terms of solutions, what you get here is the cell density in green, the pressure in blue, and what you see is that you have these fronts which are propagating and which correspond to what you observe in experiments. So this is a spheroid. When you have a spheroid, so which means you have cells which are grown from the center of the experiment, and they are growing. You see that you have this kind of growing spheroid, and what you see is that the cell density in the middle is more or less constant until you reach the boundary here. So this is the center of the spheroid. This is the boundary. You have a boundary, as you can see here. And what you are missing in this model is that if you wait long enough, the cells in the middle here will begin to die, because the spheroid is growing. The nutrients, these are experiments in laboratories. So the nutrients arrive from the boundary, but inside there is no nutrients. So cells at some point, cells here have not enough food, and they begin to die, which you cannot see in this model, because we did not include the nutrients, by the way. So you can do it. The second step is you say, okay, I keep the same idea of a porous medium. My growth now is controlled by pressure, but also by a nutrient, because cells need oxygen to survive. And I have an equation for the nutrients. So diffusion, because you think that there is diffusion through the tissue, and there is consumption proportional to number of cells for maintaining the metabolism, and then there is a release, except because there is an experiment and there is a flow outside, or because you have blood vessels which are bringing the nutrients. So you are back again to this system, like we said for Fischer-KPP, this system of two equations. And what you should observe from that is what you see experimentally in a tumor, that in the middle you have necrotic cells. So these cells are dead cells in the middle. They have not enough nutrients and they died, and they are in the on this annulus there is these proliferating cells, this proliferating rim, which have access to the nutrients and which are dividing. So this is what you can observe in experiments, which is this necrotic core and this proliferating rim. If you put in a computer the solution of this equation, what you observe is this. At the beginning, your cells are dividing like a spherical wave. There is food, everybody is happy, they proliferate, they grow. And at certain time, these cells which are proliferating on the boundary, they use all the nutrient. So there is no food in the middle, cells begin to die in the middle. And if you continue, then the middle are completely dead. You see very well this proliferating rim. And if you continue, in certain circumstances, you can see that it is creating instabilities. So these phenomena can be the reason of the instabilities that you can observe in certain tumors where you have this phenomena. So nutrients, as soon as you put nutrients, now you have the necrotic core and the proliferating rim, and this becomes realistic. It is caused by the nutrients, which is at the external. So the intuition I can give on that, if the nutrient is coming from far away. So in fact, to do that, the nutrients arrive from the boundary. So if some cells have, for some reason, an advantage here, they will be closer to the source of nutrient. So they will divide faster than those which are behind. And because there is diffusion, because the nutrient arrive by diffusion, all this food which is used by the cell has an impact on a small neighborhood. And so all around there is a shadow without nutrient. So these cells will continue to grow faster because they're in front. Those which are behind, they even have less nutrients, and so they will not progress at all. And so this enhances the instability. Okay, so this is, by the way, this is what you see in the model that Lenya Rijik was describing last week, which is the thermoreactive, the thermochemical reaction. So in chemistry, it is very well known that you have this kind of instabilities for the same reason, is that if you have a temperature which is increasing with a chemical reaction and a chemical product which is consumed by the reactant, if the temperature diffusive if alpha is small, then this creates instability. So this is the case, the difficult case that Lenya was mentioning. He mentioned that there are two cases. Either alpha is large, and it's easy because you have a comparison principle, or alpha is small, and this is difficult. So this is a difficult case where you see these instabilities. And for me, it's nothing but Turing instability. So Turing tells you that if you have a right-hand side, okay, for Turing it was a linearized right-hand side, and if you have the two viscosities which are very different, then you can create instability, even though the system here is stable. The ordinary differential equation is stable, but the diffusion makes it unstable. So this is Turing observation. And this is, by the way, who knows about Turing instability? Who has heard about that? So this is something which I'm very surprised because for me, if you tell me what are the big results in PDEs in the 20th century, well, because we're in the 21st, we can ask, okay, what I would tell you is there are two results which are amazing in PDEs in the 20th century. One is Lax-Milgram, which tells you that to solve a PDE, you need to build an Hilbert space, which I think is very surprising. And if you want to solve it, you have to fill the Hilbert space by beautiful functions. And the second one, for me, is Turing instability, which tells you a differential equation can be stable. You can add a viscosity, which is a stabilizing effect, and the result is unstable. So this is what I would say about the most surprising results in PDEs. Oh, if alpha equal 1, it's easy. No, if alpha equal 1, no. Alpha equal 1, you will not see this beautiful... alpha small. Alpha small. Oh, no, I don't think this is... okay, let me think about that. This is, isn't it true that Who spoke about that last week? There was a talk on that last week. Not stated as you said, but there was a talk exactly which was related to this question. It's a very difficult question. No, it was not stated like that. But it was. But no, I think there is no way in these kind of things to know what is the length of these digits, what is the distance between these digits. It's very, very complicated. I don't think so. There is a famous paper by a physicist who passed away a couple of years ago, Ben Jacob, where he has a theory for that. But it's not very, very convincing that you can do something really serious in terms of mathematics.
Instability into simulation, it's different from PDE and it's different from your scheme. How do you know which one is from which?
Okay, so that's a surprising effect. That, of course, if you make a very fine grid, and then you will get the spherical shape longer and longer. But when you look at a certain time, the pictures are always the same. The length, the distribution of the instability is always the same. So I think that the way you have to understand it is that you have a linearized instability, which creates something, and then the nonlinear phenomena takes over, and that dictates the length of the digits, the distribution of the branching, and so on. And so this is a nonlinear effect, which I don't understand really what it is. But if you do, you look at different teams are doing different numerics with different codes, they get the same pictures. So this is surprising, but this is like that. So this explains this kind of phenomena that you can see in instabilities in tissues. What is the next step?
But in your model, what's the C? This model, precise. What's your function C? Close. Yeah, Laplace C.
Oh, sorry, it's a mistake. It's S. It's S. It's S. Yes. Okay. So maybe this will be a little bit too long. So it's already 11. So I suggest to stop now for the break, and we continue afterwards with more elaborated models. Okay.